Yesterday we have basically a very exciting overview of the course, and I think we have covered both cyber security, cyber space as well as machine learning space. So today Professor Mishra will cover in the first half the hardware acceleration of explainable AI. I mean how do you implement these things in hardware, right? So those part, and in second half mostly on the malicious softwares, malware, antivirus, and then malware detection using explainable AI, right? So it will be another exciting day to hear. I just want to say one thing. So when you ask question, use the mic in the row, so then the question will be also get recorded. Okay. So we try to use this particular recording for future usage, right? So if you ask a question, that should be valid questions, and that would be discussed in the course, right? And it will be recorded. So please use the mic in every row. There is a mic. You can just take it to you and talk on the mic. Okay. So that will help. Okay, so thank you. About you.
Good morning, everyone. Let's welcome to the second day. So today our focus is on talking about explainable AI, but one of the important aspect of explainable AI is that because it's trying to explain something, it has a lot of material in it, and if somebody wants to use it, it's going to take a lot of computing resources. So most of the systems, whether you think of car or medical equipment, they have to make real time decisions. Explainability is wonderful, but they should be able to finish in a real time as fast as possible. So if some computation take too long, only way you want to accommodate in real time systems is by making them execute faster. One way you make them faster, you use some hardware based acceleration. So I am going to talk about how do we accelerate explainable AI, but some of the concepts I am going to talk about, I did not want to make an assumption if you already have a background on acceleration or speeding up. How many of you have done any acceleration of anything? Let us say you wrote a program and you tried to make it faster. How many of you have tried it? One obvious way is doing.
I reduced API calls to scripts and also those kind of acceleration using software.
You can reduce the calls, a function call, by replacing the function body. You put the function body there. You can make for loop execution by unrolling the for loop. There are things even in software level, many of you either used or are going to use multi-threading, trying to do parallelism. Parallelism is one way of doing acceleration, but that's you are doing acceleration with the processor itself. So in the first part of my story, I am going to talk about how the processor architecture itself can help you in acceleration. I am not going to introduce multi-threading, that is a software level technique, but in the hardware level, if can I make any changes to my processor itself, so that my programs can be executed faster. Then I will talk about how about dedicated hardware like field programmable gate array, graphics processing unit, tensor processing unit, how do they help us accelerate. So the first part of the discussion is going to focus on how do you accelerate things, and then we will use those technology, or at least depending on the time, one or two of them, how do we then accelerate explainable AI, what does it mean. So let us start with the architecture. If you have taken any courses on computer organization or computer architecture, you kind of then know that there are kind of pipeline, the execution pipeline you think about where your program runs, that basically have some form of, it fetches some instruction, then it decodes the binary instruction, then it executes them, and there might be memory stages, or may or may not, or execute might cover that, then you write back to a register file. And how does this connect to the big picture? Remember when you wrote a, let us say a C or Java program, that get compiled in a compiler, and that compiled code is actually bunch of zeros and ones, that binary, those binary and data, whatever that or assembly program, whichever way you look at it, that gets executed through this processor. That is the key idea. Now how do we speed it up, this execution? I am zooming into this execute part. So that zoom, I am zooming and this idea is not new. This is from 1960s in IBM, the vector processing, and when I was doing my undergrad, we had to learn a language called Fortran. Fortran, COBOL and all these languages. How many have heard any of these languages? Fortran. What does Fortran stands for?
Yeah, I usually heard this term. I don't know.
What does it stands for? The name, where did it came from? Formula translation. So, this Fortran or any of those, it has lot of this nature addition, A equal to B plus, a lot of computation. Only difference is you might say, oh, that's I write program like that. No, you do not, because these variables are vectors, arrays. So, this could be an array of 100, this would be a B of 100, and in this interest of space C is 100. This is 100 elements it is trying to add. So, if you are trying to add 100 variables of 100 elements, can we make architecture faster? So, then IBM solution was, how about instead of having one register which is storing one variable of 32 bit, can I store multiple of them in the same register, so that in a single addition call I can add multiple of them. It would be nice if this register was 32 multiplied by 100, but that is not how it is. It is typically some multiple of 32, but not 100 or 1000. Anybody knows why not 100? First of all, binary power of 2, that is interesting. Second of all, in your program, if your array size is 100 or 15 or 13 or 11 or 19, processor designer cannot design for that, right. They will design for something, you have to wrap it around. If this one is a multiple of, let us say, a multiple of 32, if you are doing 100, so then you have to do one call that will cover 32, you have to do another call that will cover another 32, you have to do another call that would cover 32, and then that covers your 96 plus the last call you will cover 4 of addition of 4 of them. So, basically last call you are going to waste, although you have 32 locations, only 4 locations will have valid values, all other locations will have bunch of zeros, nobody will care them, right. But that is the idea, that instead of making a for loop iterating 100 times and you are adding each time one element, here in a call of 4 I am able to add them. That is the idea, and because you have less number of instruction, less read after write hazard, write after write hazard, branch prediction, all those goes down, that gives you the speed up. Any question on this basic idea, that instead of adding 2 elements at a time, we can add more elements at a time, and this is only useful when your program has lot of vector operation. If your program has scalar operations, then even if you have architecture like this, it is not going to help you. You are just wasting your resources. If you have 32 locations in this register, only one of the location will have value, everything has zeros and nobody cares, that is not a good idea. Now, I want to show you the code. What I am trying to do is I am trying to compute y equal to a times x plus y. A is a scalar value, think of 5, 10, some number, x and y are vector arrays, and this is in MIPS code. So, it is not important if whether you have done the assembly. So, it is basically you are loading the value of a into a register, then you are adding, then you basically loading the value of x, you are multiplying with y. So, this particular one is done with a times x, and then you load, then you add, then you store, add this load is you are loading the location y, and then when you add, this add is a times x plus y, when you store, you are storing into y, and then these are basically adjustment of the array pointer. So, for example, here is the x array and it has all these elements, here is the y array, all these elements. So, the first pointer points to the first location, this pointer points to this location, this pointer points to this location, all these are basically you are incrementing by 8 bytes, because it is a double operation on the double, it is all of them are 64 bits, that is like 8 bytes. And so, 8 bytes you increment, then you do the loop bound, you take care of it, and if its loop is not 0, you go back. So, you are doing this for 100 times, and there are, because this is, if you count 1, 2, 3, 4, 5, 6, 7, 8 and around that kind of stuff, you multiply by 100, you are looking at about 600 instruction. If you do in a normal way, normal processor, each register is 32 bit or 64 bit, that is how you compute, is going to do 600 instruction. If you have the architecture I showed in a previous slide, then in a single load you get the all of the variable x. In a single multiply, you multiply all elements of x. Think of, you have values 5, 10, 20, whatever values. If you are multiplying by a, let us say a is equal to 3, you are multiplying everybody by 3 in the same shot. So, this become 15, this become 30, this becomes 60 and so on. In a single instruction of multiply, you are multiplying all elements of that array by the scalar value of a. That multiplication is done, then you load y, you get the whole array in a single shot, and then you add, you are done with that. And so, basically now you are looking at about 6 instructions, 6 versus 600, that is the speed up of 100 times. Any questions? Use the microphone please. Yes please.
Sir, so in these kind of architectures, a larger ALU is required.
ALU has to be larger, thank you, and the register also has to be large to accommodate this. And in reality, as you realize, in your program you can define any vector size, but your architecture may not support it. So, that is where there are practical limitations to that, but yes, you need that kind of structure. So, the practical limitation I wanted to just show, in a typical architecture you have all these array elements and this one ALU which can add only 2 32 bit numbers at a time. So, if you have 9 locations, you need 9 clock cycle to perform, but if you have 4, unless you have 9 parallel adder, you can't do in a single clock cycle. So, for example, if you have 4, somehow this 9 you have to divide in this manner. So, you need at least 2 clock cycle. So, depending on how many resources you have, that is how it is going to go. Even if your register size is big, if you do not have the ALU of that size, it is not going to work. But that is a practical limitation. For this discussion, we are going to ignore, and as you realize, there will be practical limitations. In the previous example, I talked about 100x speed up. In reality, 100x will not happen. That would be determined by how many parallel computing resources you have, and that is fair expectation. If you put 4 employees, you can't expect 100 times speed up. If you put 100 employees, you may not get 100 times speed up, because people are not friendly, they have ego and all that, manager, interdependency, people become sick and all that. So, 100 would be your maximum expectation. Same thing here. As you can see, you have 4, but you are not getting 4x speed up, because there would be time when there would be nothing, because when you divide, there would be time when some computation has to be stalled. So, that is about the architectural modification to accommodate vector operations. That is the vector architecture. Now, I want to introduce one more architecture. In 2000, Intel introduced it, and the Intel SIMD extensions. So, the idea is, okay, instead of telling the idea, let me ask you a question. How many of you played or used any data set that deals with audio or video, directly or indirectly? I am expecting all hands, because that is most of the people waste their time on, playing video game and going and browsing through, what is it called, reels or whatever those are. That is all about multimedia data, audio, video. In fact, most of the data, 99% of the data in this world is audio and video. There are few backdated people like Professor Korfa and I, who are so backdated, we deal with scientific data. Most of you guys are smart and advanced, you deal with multimedia data, which Dr. Korfa and I think are useless, but you will figure it out in another 20-30 years, how you want to waste your time. But that is not the discussion here. Let us zoom into multimedia data. How do you think multimedia data different from scientific data? Scientific data like these instructions we are doing, 32 bit instruction, how is it different? Do you think there is any difference? Let me spell it out for you so that you can answer me. directly. So, let us focus on multimedia. There are lot of types of data. Let us focus on two types of data, audio and video. And the type of data we deal with, which I think normal people like me, we deal with 32-bit or 64-bit, let us say integers. That is what we deal with, scientific data. Do you believe audio video data is any different? You can define a variable x and you deal with that, or you think they are different? How many of you think they are same? How many of you think they are different? Why do you believe that is different?
So because the way of representation is different. For an audio file, sir, I am.
But you are defining a variable integer. For the computer, what difference does it make?
Yes, if I with that variable I store an audio file, it will be kind of the same for the.
It is different. It is different. Video data. What are you storing in video data? Let us focus on video. What am I storing? Let us say I am comparing faces, right? Whether in my brain doing or machine learning is doing, or a military aircraft trying to find a target to hit a bomb, they have a picture of the place, and then they are taking picture real time, and then they are comparing. So, pixel by pixel, millions of them at a time. So, each of these pixel, anybody knows what is it represent? Do you guys deal with 99% of the time, waste you time with this and you do not know what you are dealing with? Each pixel, what is it? RGB values, right? Thank you. Now I don't, I am okay that you guys are wasting time, at least you can say. Now let us go to the next term, RGB. What exactly, how many bits representation it is? What does it capture? Intensity, and intensity ranges between 0 to 255. So, each of them further if I divide, it is a intensity which ranges from 0 to 255. How many bits do I need to represent 0 to 255? Then did we decide the 8 is not equal to 32? Now, if you add lot of 8, then it may become any number. Remember, these are millions of pixels, each has RGB multiplied million multiplied by 3 RGB multiplied by 8, that is a lot of them, or even if you focus on each pixel, 3 multiplied by 8, that is like 24 bits, it actually has more than RGB values in reality, depth and all that, but each of those element is 8 bit for video at the smallest level of granularity, and R value has nothing to do with G value, they are independent of each other, they are not even cousin. They are not cousin brother, cousin sister, right. So, when you are comparing two images to see it is a perfect fit, you are really comparing R value of this image with the R value of that image. So, you are dealing with 8-bit data. If you are dealing with 8-bit data, if this is a 64-bit register, if 8-bit would be sitting somewhere right here, all of the values would be 0. Is that a great idea? That is a bad idea. You are wasting the resource. And Intel in 2000 realized that people are, for any computation, any program people write, they are going to deal with lot of audio, video, multimedia data. So, we need some mechanism where we can do, we do not waste this kind of resources. So, they want to take advantage of those resources, and they came up with this idea, can we put multiple of those words. So, for this one is for the audio example, so I will come to that, but I want to tell you the idea that I should be able to capture 8 data here, 8 cross 8, 8 data from 8 different pixels in the same register, 8 data from 8 different pixels for another register. In memory, each of them stored as 8 bits, so there needs packing instruction, unpacking, all that I am not discussing. But in a single load you get the data, but this data has nothing to do with this data, which has nothing to do with this. If you add, addition will continue, you would be able to add word 3 of this one with word 3 of that one, that is the idea, right. So, you do better utilization. Now, for audio, I do not want to spend this much of time discussing audio. Can anybody tell me what is the size of the data, audio data?
Depends on sampling size.
Nope. What is the number? I am looking for a number. It is a fixed number in the world, and it is determined based on what you said. So, your answer is correct. Sampling frequency is important, but what is that sampling? Actually, it is not sampling, it is the quantization. How many bits used? It is 16 bits. I told you, right, this is for the audio, I gave you the answer. For audio it is 16 without spending too much time. Why it is 16? Because Nyquist's theorem says that if you represent an audio data with 16 bits, the waveforms that you will be able to capture, that is human audible range. If it is for a dolphin or cat or dog, they might have a slightly higher frequency they could be able to hear, but for human audible it is basically the 2 to the power 16 space is more than enough. Unless you think you are a superhuman, you can hear things from other galaxy, that is a different story. For most of us 16 bits, that is why all audio data in the world is 16 bit. So, that is why in this 64 bit representation you have 4 of them. Just by looking at it, can you tell me what is the speed up here? Because we are talking about acceleration using SIMD architecture. What is the speed up here? Everybody nodding head? 4 times. In this audio example, instead of putting one word and everybody 0 versus putting 4 of them, I am making it 4 times faster, because you are able to do 4 addition in a single shot. Of course, as I said, packing, unpacking, the initial overhead, if you ignore that, how do you load the data in the memory in the first place? So, then it is a 4 times improvement, that is the speed up. Any question? Only thing I did not still tell you, which is this adder. Remember, Intel came up with this idea, these instruction set extensions for multimedia instructions. This adder most of the time would be used for normal operation and once in a while for multimedia instruction. Do you see a different how this dude would have a problem dealing with them? Carry overflow. If all of the data is same, then carry will propagate from each bit to another bit, but because these data are independent, the carry that is coming from here to here, that should not propagate, 0 should propagate, because this word and this word has nothing to do with each other. That is why I will show you a modification. So, this is a 32 bit register, each 16 bit. This is actually Hewlett Packard precision architecture, and if you can see the carry propagation between the stage has this multiplexer, and the selection line, am I doing normal add or half word add? If I am doing normal add, then it is basically going to send 0, and if it is a 0, it is going to select the top line, which is whatever was the carry, it will propagate through. If I am doing half word add, then 0 will propagate through. How many of you have questions? Because if you, I am going to ask you a question now, I am expecting all hands. In this story, how many multiplexer would be needed? 3. You are not supposed to answer. 3 multiplexer would be needed, 1 in this boundary, 1 in this boundary, 1 in this boundary. Then the same adder would be able to be used as a full adder and as a multimedia adder, same architecture. Of course, the assumption is we are doing ripple carry adder. If you do carry look ahead adder, carry save adder, all that design will not be supported here. So, now if you go for the SIMD code, I will not get into the detail, but only thing I wanted to say, SIMD gets you 4 times reduction. This should not be a surprise. I am able to accommodate only 4 data into one register. I am able to add 4 of them at a time. So, that is going to give you 4 times compared to 100 times in vector architecture. Of course, we also discussed there, it is not 100, it depends on how many parallel ALUs you have. Typically, it is 64 ALUs in IBM architecture those days. So, then it is 64. So, through architecture or through today's processor itself, you will be able to get speed up only if your applications are multimedia types. In case of SIMD, if it is of vector, a lot of array operations, array addition, array subtraction, then vector architecture would help. If none of the above, then only help would be multi-threading, but even then compilers should be able to find lot of parallelism in your code. If you wrote a code in such a way, every statement depends on the previous instruction, then multi-threading will not work either, but that is still a possibility. Before you go for any acceleration, you want to think of what can I do with my current processor itself. Any questions? So, this is basically kind of I am going to talk about. So far I talked about how a processor itself would accelerate your application. Now, I am going to talk about how field programmable gate array, a dedicated hardware, is going to help you. Now, in a bigger scale of things, I want to discuss 3 distinct choices in design. One is the CPU or processor I talked about, one extreme. Then other extreme is ASIC or application specific integrated circuit. FPGA is somewhere in the middle. So, in terms of flexibility, CPU is the most flexible one. Using CPU you can run anything. If you can write a program, you can run anything. Using ASIC, that is not possible. ASIC basically you hard coded design something. If you design an adder, all of its life it is only going to be able to add, that is all it is, nothing else it can do. On the other hand, FPGA is a reconfigurable fabric, which I am going to talk now, which you can do, you can change, but it is not as flexible as CPU. So, from a flexibility index, so this is basically the flexibility side, more flexible. And in terms of efficiency, energy, power, performance, this is the efficiency side, this is the thing. So, processor is least efficient in terms of acceleration, energy efficiency, speed, whichever way you look at it, power. If I want to make it little kind of what do I call silly, this is our example. Let us say I wanted to implement a picture like this. Of course, it does not matter what this picture is. If I want to implement this picture, that is all I wanted to do. I did not do it right, but if this is what I wanted to implement, let us say this is a design of something, then an ASIC will exactly design that. That is your ASIC. Let me write that deep inside. This is ASIC. You exactly design whatever is needed. Now, how the other folks will look with respect to this? Let us choose red. No, it was red. Let us choose purple. If you are talking about FPGA, FPGA probably something like that is probably is FPGA, all of it. So, it can accommodate other structures also inside like multiplication, division, but it is slightly bigger. If all you wanted to do addition for rest of your life, using FPGA you are wasting some resources. The reconfigurability that you provide, that comes with the cost. If you are thinking of CPU, if you really wanted to make close, maybe instead of square, let me take another color. So, instead of square, it is kind of going to be a, so that is probably CPU. It is much more bigger, lot more features, some of them you may not need. So, let us say it has a floating point operations or floating point execution unit, but the thing floating point may be not there even in the program, but you are still paying for it, it is still consuming energy. If you say, oh, I will do shutdown and power management technique, that power management logic also is going to take you some energy. Let us talk about field programmable gate array. And so basically in the previous discussion, as I talked about CPU and its power, now I am going to talk about how reconfigurability is going to give you the benefit. It is a lot of information and text, I will straight go to the reconfigurable. The idea of reconfigurability or field programmable gate array is that you have lot of elements, repetitive elements of computation node and then some form of communication. And if you go back to your childhood, I do not know whether you played, we played that you have bunch of numbers or bunch of cities, and then you have to, let us say this is Kolkata, this is Chennai, this is Mumbai, and there are all these places, and we have to go from city A to city B, and there are many such connections you have to make without overlapping. Let us say there was a requirement Kolkata to Chennai, and you can choose any path. So, this is computation, you can start from here, one of the middle places, but then you have to choose one of these paths to go to Chennai. Now, let us say from so you go to Chennai, from Mumbai, let us say I need to go to Delhi. So, then you have to choose how do I go from here, and then without touching maybe this side is not allowed. So, there is no way, or at least if I come this way, there is no way I can jump through or go through any kind of way to connect Delhi, but that is what I want to do. So, this is communication reconfiguration. When some computation going on in any of these computing elements, which I will show in a moment what happens. I am going to show you what is the computation reconfiguration, but communication reconfiguration is also needed, because you are doing lot of computations, but they are related. You have to connect those, or one computation is producing something, another computation is consuming, you have to make that connection. So, communication reconfiguration and computation reconfiguration. So, next 5-10 minutes I will zoom into computation reconfiguration, but I want to ask you, is it clear this communication reconfiguration problem? You have a lot of computation, one of the node will not be able to do, you need lot of nodes, actually you need millions of them, and then somebody is producing something, somebody is consuming something. That is like our childhood game from Calcutta to Delhi, Mumbai to Chennai, all those connections you have to make. And how do you make it without the crisscrossing each other? What does crisscrossing mean? Some data is flowing through zeros and ones, you want to throw some more data on it. In general, it is not a problem. If the size of that bus, let us say is 64 bit, then two sets of data can communicate. If size of the bus is 32, we can still communicate. Anybody knows how? If two people each has a size of 32 bit, wants to use a bus which is also 32 bit, how do you do it?
Simplex mode of computation.
Multiplexing, time multiplexing you do. So, you have still bus, physically think of a bus. In the morning we use it, in the evening maybe IIT students use it. So, as long as that they are not needed exactly same time, it is all right. But what if two computing nodes are producing the data exactly same time and two other nodes needs exactly, then we have a problem. That is why the way you place the computation, that is also a difficult problem in FPGA. So, although I am talking you to FPGA fabric, but to get the speed up, you do not get the speed up if all those things are not done right. Now, most of the things you do not have to worry about, because whichever FPGA you are using, Xilinx or Altera, and it is not a surprise, these companies were flourished before Intel bought Altera and AMD bought Xilinx. And whatever the story is, if you use their tool set, they will take your design, break it down into pieces, map it to these nodes, place them correctly, route them correctly, configure them correctly. Once they are configured, they are going to run almost at the hardware speed. Processor going to the programs that you are going to run, it is still the speed you are going to get millions of instructions per second. Here it would be able to run billions of instructions per second, actually in gigahertz you will be able to run here, because it is hardware, FPGA is a hardware. Now, each of the computation, the configurable logic block, I am going to zoom into the computation reconfiguration. Each of the if you further zoom in, lot of size slices, lot of connectivity. If I log into the slice, only thing I want to show you, how is it magically possible same computation node can do addition right now, subtraction 5 seconds later, does it have all the adder, subtractor, multiplier like ALU? No, that is one way of doing. You have all that thing, you select one of the things, but FPGA does not work that way. So, to show that, I created a funny story here. This is actually not real, this is actually not how it works in FPGA, but I thought of how do I show it to you. So, truth table, I hope all of you are comfortable. This is an AND gate truth table, you have input x and y and output z, and let me draw an AND gate. So, this is an AND gate and we have x and y and output is z. Look at the truth table if you agree. If it is 1 1, then output is 1, otherwise output is 0. I am trying to implement using multiplexer. So, if you want to implement exactly this magic logic inside this box, x and y is input, z and output, I have to use x and y as the selection logic for the multiplexer, and this output of this truth table, these numbers here is exactly same as this number here. That means, if x and y is let us say 0 1, I want output 0 and it is going to select the second line and output is going to be 0. Convince yourself this will perform AND operation. If you are convinced, all I have to show you, if 5 seconds later, 1 millisecond later I want to perform the OR operation, only thing I have to change, whole structure remains the same. Instead of this truth table, I have to just provide the output of this. I have to replace those values with these values. I will come in a moment how do I do that. I have to just replace those values, that is it. Somehow if I can do that, I reconfigured that computing structure to do OR operation. If I want to do XOR, same story, I just replace that original value with the output of XOR logic. Just convince yourself that this structure is exactly the same, only thing different is this 4 cell memory logic here, those values are different. If I can supply those values, that is my reconfigurability of the computing logic. Again for the disclaimer, this is not how FPGA is implemented. I just wanted to show you how can you use the same logic, same lookup table to do whatever you want. If you are convinced with that, then the big picture is when you write a design in Verilog, VHDL, whatever is your favorite hardware description language, in our case explainable AI logic, I am taking a simple expression, and then once the Xilinx or Altera compiler compiles it, it produces bunch of zeros and ones, we call it a bit stream. Exactly the way when you compile your C or Java program, it produces either Java bytecode or assembly, that you apply assembler, you get the binary. Here the same analogy, you do the FPGA synthesis, you get this, and coincidentally these colors are not random color. These values are for OR operation, these values are for AND operation, these values are for XOR operation, and this is also, these values are also not random, this is exactly the output of those truth table. So, for example, look at 0 1 1 0 for the XOR, and let me go back to that slide. XOR, the truth table output is 0 1 1 0. So, if it is a 2 input, that is the exact truth table output. So, synthesis tool produces exact that, and then when I want to do reconfiguration in the FPGA, remember each of them is a configurable logic block. So, then I have to just map these values 0 1 1 0 for OR operation, this is 0 1 1 1, this one 0 0 0 1 is this one is. So, this is basically doing the XOR, this is doing AND, this is doing OR. Sorry, 0 1 1, oh 0 1, oh, a different color would help. So, that is maybe white will help. 0 1 1 0. So, typographic problem. So basically it is exactly implementing this, only thing remaining is now this communication reconfiguration. In reality this is not how it is done, it goes through these boundary lines, but I just connected it just to show that this will produce something that feeds to the first one, this produce something feed to the someone, and this final output A B C D, yeah, final output is A in this expression, that is basically the final output. And again this needs to be routed through all the way to the primary output. Let me go back few slides just to show you, if you, so the finally let us say whatever the final computation is, that need to be somehow, that should be routed, from that it needs to be routed through one of these pins and final output, that is kind of downloadable. Any questions on FPGA or reconfigurability? So, what is the bottom line? We are going to use this fabric to speed up our computation, to speed up our explainable AI, and there are a lot of work. If you want to pursue this line, there are a lot of work. How do you take AI algorithms? So, I keep talking about explainable AI, but even AI acceleration is also important, people are doing it, and that is also done, most of those acceleration is done through either GPU, which I am going to talk, or TPU or FPGA. So far I talked about how FPGA can speed up the execution. Now I am going to talk about how graphics processing units can speed up the execution. As the name suggests, graphics processing unit is basically designed for graphics, and all of this started from a company called NVIDIA 15-20 years ago. And remember 2000 Intel came with multimedia instruction extension. So, for every add instruction there is a add byte, add half word, add double word, there are so many instructions they came with. What NVIDIA realized, if everybody except Dr. Karfa and me, if everybody is dealing with multimedia data, why do we take a computing core that is designed for scientific applications and try to change it to do graphics processing, or why not design something for multimedia processing, and if Dr. Karfa or I want to do scientific computation once in a while, it is okay, because that is least important. If the whole world is interested in multimedia data, let us design something from, what is it called, from ground up, let us design something for purely for multimedia speed up. Now, it is kind of seems silly, explainable AI and all that is kind of scientific computation, how come GPU would be useful, we will discuss that later, but I want you to understand the processor philosophy or vector architecture, you are still building on normal architecture. The Intel the extension also building on normal architecture and trying to change it to accommodate something, but if the one you are trying to accommodate multimedia, if that is 99% of the story of the world, let us design an architecture for multimedia processing. And the NVIDIA became multi-trillion-dollar company. One of my PhD students became billionaire, because you join a company right on time and that company has to flourish, become multi-trillion-dollar company, then you become billionaire in no time. He is a chief architect of NVIDIA. But the point I am trying to make here is not the money, point I am trying to make here how NVIDIA became successful. I want you to understand, they saw the market, even then they were struggling. I knew day to day what is going on, they were struggling, they came up with the architecture or design, they do not know what to do with it. They were giving us money, the professors, what are you working on, bioinformatics, okay, try running this on bioinformatics and see if you can do something. They are giving people money, free GPU set for you to do experiments. So, medical people, bioinformatics people, biology people, science people, maths people, every architecture people, compiler people, everybody getting GPU, they are trying to apply and nobody is seeing any success. And inside there, internally in the company, they were trying to implement something called CUDA programming language. They quickly realized there is no way you can provide all these parallelism, and in fact we were happy, we got used to the idea that I have a GPU of 1024 cores and we are getting 5 to 10 times speed up, we were happy with it. Do you see the funny thing? You are giving me 1024 cores and I am getting 5 to 10 times speed up. That is like you can look at it as a 100 times 10 times speed up, or you can look at it as a 10 times slowdown, 10 times of the resource wastage. So, very quickly NVIDIA figured out in couple of years, scientific computing speed up and GPU, that model is not going to work, or in a desktop processor putting some NVIDIA GPU, they will not be able to make a lot of money. So, then they came up with this CUDA development environment. Even then this programming was really painful. I will show you a CUDA program. This is how CUDA program, and we were writing by hand. So, if remember that x equal to a plus b, a equal to b plus c, to write that thing you have to write all this stuff. So, it is actually lot more pain than writing normal program, and again NVIDIA figured out this CUDA programming is. So, basically instead of compiler finding the threads, a equal to b plus c, each of them is a vector, you break it down into how many vector, how many element, and you are saying okay, there are each thread has this, you are basically extracting the thread, writing them yourself, that is not going to work. Then came the ecosystem of Python library and PyTorch that would automatically generate CUDA programs, you will not even know, you do not care, then it would map and run on the GPU, this whole ecosystem got developed, then that is basically the boom. So, for you to start a company and become successful, you have to do a lot of stuff, many years you have to spend. Even the VMIPS example I talked about, the original architecture was MIPS, even before that the predecessor of that architecture was DLX, and it was designed by none other than Hennessy and Patterson. Hennessy is the Stanford president, is or was the Stanford president, Patterson from UC Berkeley, those are topmost people. Even they could not convince the community that you going the Intel route, complex instruction is not a great idea. So, if you want to really speed up and low power computation, this is the great idea. What did they do? They took leave of absence from Berkeley and Stanford, they started the company, made it successful, then people got convinced, and eventually they got Turing award and became Stanford professor, that is a different story. I am just telling you, even this acceleration and speed up story, if you really see the back end story of it, the journey is not pleasant for even for people like Hennessy and Patterson, they had to go through all of these. Of course, end result is wonderful. And then MIPS, related to those of you who are following these days, Intel AMD architecture or ARM Intel AMD, those are the general purpose, and then RISC-V is the kind of community academic open source kind of variant, that is what you are talking about, and I will talk about this also one of the lectures. But this is the CUDA programming, this is what it used to be, but the ecosystem got changed. So, that is why you do not have to learn CUDA programming anymore, but what you have to do is basically, this is one of the old one, this is the Fermi is 2010, this is the these are the internal code name, this is not what you buy, but right now they are selling Blackwell, that is like really expensive. So, I think G-Force or maybe one of those A100, that is $30,000 a piece, $20,000-$30,000, these would be even more expensive per piece, Blackwell, next coming Rubin. So, these are the movement, and I will show one of them, maybe I will show you Fermi and Pascal, just to show how is it different from the fetch, decode, execute, where is it giving you the speed up, what is going on, what is the magic, that magic I will spell. But this code name and variation, this should be same as even in the processor world, the 8086 there are many variation, Pentium 5, 6, NetBurst, Intel Core, and I did not list all of them. In the GPU side the same story. So, I am going to zoom in, before I zoom in, do you have any question? So, as you can see there are a lot of parallelism right there, this remember the SIMD, that was the reason I explained you that SIMD architecture, because it still implements that SIMD single instruction multiple data architecture model, and if you zoom into SIMD it is nothing but an integer and floating point unit. But there is a lot of parallel computation node, and the model is different, instructions are getting pushed from this way and data is getting pushed this way. This is not the von Neumann architecture that we are used to. In von Neumann architecture, instruction is the boss, data comes to the processor, that is the assumption and idea. Instruction flows through the pipeline, data comes from memory, hard disk, and travels. So, instruction is the master in a master slave architecture, data is the slave, but in a multimedia world 99% of the story is data. So, data is the boss, why should data come? Instruction should come to the data. So, then before GPU happened, there was a world of memory based computing or computing in memory. Instead of data coming to the instruction, why not instruction goes to the data, why do not we compute in and around memory itself, but that did not go too far, that still has lot of good applications, that did not go too far. Here data is getting pushed from this side and instructions are getting pushed from this side, and there are lot of parallel load store, there are memory at the SIMD level, there are and so that is one speed up, data and instruction coming through, one speed up. Second is you have to understand this is actually doing vector architecture. GPU is not good if you have too many if then else and we are operating on few bits or few bytes and trying to compute some control flow, GPU is not good for that. GPU is good for data level parallelism, lot of data level parallelism, not instruction level parallelism, few instruction, lot of data. Remember in vector architecture it was also good for the same thing. You have one addition, but it adding arrays of size 100, 1000, 5000. So, lot of data, few instruction, that is the model, data level parallelism. If your program or the domain, do not throw GPU wherever you feel like, do not do that. It only flourishes when there is a data level parallelism, lot of data, lot of this is another. Second thing is in normal processor, operating system handles all these task scheduling, moving thing, context switching, all these stuffs are gone. All that scheduling and all that are done right here, thread scheduler, everything is here. Think of operating system, million line code operating system got minimized into few 100,000 lines of code, even then that was converted to hardware, that is not even running in software, that got converted to hardware. And these thread scheduler thread, remember I showed you a CUDA program, let me see how far away. So, each of them is a thread. If you wanted to add 100 elements, so it will create 100 of these, I is so 0 0 0 1 1 1, it will create 100 of this is called thread. One individual element addition in a vector is called a thread, and those threads is going to schedule, is the thread 1 going to be executed here or there, and then also it will make sure the way data is coming, the instruction and data they get closer to each other, so that they do not have to cover long distances through this communication path. So, minimize communication, data and instruction both glues together to the computing node, and as soon as results is done, data get transferred to the node that wants to use it, and they will be placed even nearby as possible. So, some of the ideas of FPGA that also gone in here, the placement logic, some operating system got out of the story completely, and this is basically how it is, the GPU, standalone GPU. But in the real world, people use a heterogeneous architecture, which is you have a CPU or kind of fetch, decode, execute that, and you also have a GPU, and the way it is used, CPU is still assumed as a master, and GPU after fetch, if you like what you want to execute, then it is great. If you do not like, you use the help of GPU and data somehow comes back. It is like a co-processor model, heterogeneous computing model with GPU as a co-processor. Like the way most of the camera application, you have a digital signal processor as a co-processor, JPEG co-processor, GPU as a co-processor. This is mostly in your laptop, desktop story. But when we run all these AI applications, it is pretty much either you are using the GPU in the cloud or GPU in somewhere else. University of Florida has a hypergator thing, that is the largest academic NVIDIA donation. We got about initially 75 million, then I do not know how many we got. We got all these high end GPUs, 100 or 1000 of them, and we just run on them. Tons of computing node, tons of GPU, and because the NVIDIA vice president is our student, that is why we got everything for free. So, that is basically what NVIDIA or GPU story today is. Any questions on the speed up? All I wanted to highlight, why does it give speed up? Yes, please. Microphone, please.
Sir, what is the difference between CPU and SIMD?
CPU and SIMD?
Yes.
Remember we talked about in a multimedia instruction, in video we have 8 bits. Yes. So, instead of using whole register to store 8 bit, can I store in a 32-bit register, can I store 4 of 8 bits from 4 different pixels. So, then if I do add, I can operate on 4 pixels at the same time instead of 1 pixel. That is called single instruction multiple data. Single instruction is add, for example, and multiple data is data from, let us say R value from 4 pixels. That is the SIMD idea. that I talked about in a normal processor, which is also Intel, AMD, all processors today come with SIMD support, and GPU, of course, GPU will give SIMD support. Any other questions? Yes, please.
So nowadays they have GPU specific for AI computation on laptops and desktops. So do they have something different from the typical GPUs right now you are discussing on?
Yes. So, answer is yes. So, basically when somebody says it is a GPU for AI, remember in early days we were getting all this free money to explore, that is like GPU with this model. As I go along you will see. So, basically the whole ecosystem, compiler, mapping, Python code, support for PyTorch, and those function compatibility, API call, everything got customized for AI, because people 99.999% of the people are using for GPU for AI only. For AI only. If everybody is using exactly the way I made argument, 99% of the people are doing multimedia computing, nobody is doing scientific computing except backdated people like me. Similarly, even with the GPU space, even in the multimedia space, most of the people are doing AI, either AI training, AI prediction, AI this, AI that, mostly training actually. So, then whole ecosystem, tool set, chain. So, if you think of a change from architecturally, there are few minor changes, it is actually the tool set, whatever that ecosystem, so that you do not have to do too much of stuff. And if you are thinking what do you mean by too much of stuff, I need to take you back to FPGA to kind of show you something. Even today you will face that problem as we speak. In the FPGA space, let us say you mapped a design in here, and then you thought maybe I can optimize the design little bit. Let me map a tiny smaller design, D prime is smaller than D, and you try to measure power and all that stuff, there is no difference. Right? Reduce it to one transistor and map it, there is no difference, because unless you take one of the output or all the output and XOR it and connect to the primary output, the synthesis logic will remove everything, realizing you are not using any of these output. So, why would I keep them or map them, they will delete it. It took me time, it seemed silly to me, but that is what everybody does, that is one of the hack we do, so that the synthesis tool does not eliminate it. And then when I talk about electromagnetic based side chain analysis, where you place it in FPGA, controlling it is important. If you do not control it, then you will be putting your probe here and there, you are trying to measure my temperature not in the forehead, but somewhere you are touching your thermostat on that. That is how FPGA thinks, you are touching the thermostat on that door, it is not going to give you a temperature of the body. So, there are all these idiosyncrasies, GPU got rid of all these idiosyncrasies. So, that from a user perspective, you write a Python code, you hit the button, it just gives you the speed up and run. So, now I want to conclude this one, basically the subsequent one Pascal. So, as you can see the change between, I just want to show you pictorially the original Fermi in 2010 and Pascal in 2016, lot of parallelism, lot of cache. Now, then in addition to the caches and memory, in between layer also there are a lot of caches, it is just data basically everywhere dominant, and in fact if you zoom in there are caches also here everywhere, so they have different names, naming conventions. So, grid, cluster, so they have memory grid level, cluster level, block level, SIMD level, every layer they have tons of memory, data parking space, data coming in, data going out, lot of that. And then so this is 64 SIMD. If I zoom in one of those, so this is the instruction buffer, scheduler and dispatch unit, and data is coming from here, and basically data is getting, this is SIMD and this data processing. So, computing and data and load store, and I am going to skip all of that, but I want to go back and tell a story before I end. So, all of these names are of some scientist. So, I am going to highlight my favorite scientist, and I am going to ask you, this has nothing to do with GPU, and ask you how many of you know about this scientist? Those are, how many of you are from computer science? Thank you, at least somebody knows. Women's Day was like few days ago, you guys should be ashamed of yourself. First female lady programmer. There was a language we had to learn in the Fortran COBOL, there was a language called Ada, it was a predecessor of Pascal. Again that language also named after in respect to Ada Lovelace, and she was even today is the same problem, but in those days females were so utterly disrespected, they would not get Nobel Prize, they would not get any recognition. So, I think it is a high time we kind of change that attitude and figure out. She was given the task of maintaining, I guess this is the Babbage, the computer, it is a full room full of big computer, it is basically think of a calculator, a room full of size, her job like a female, yeah, right. So, they thought what a female can do. So, just take care of this thing. So, her job was to do just compute 2 plus 3 using this big machine, rotate the knob here, push that handle there, kick here and bang your head there and those stuff, that was her job. She took a notepad and tried to do little annotation, and she figured out a lot of some of the Bernoulli equation and all that stuff. She figured out we can compute lot of stuff if we do these set of steps, and she noted down some of those footnotes. We today treat them as like first program. Technically she never wrote a program, there was no programming language, but simple annotation in her notebook, and it is actually amazing if you go back and read those stories, and I actually feel bad for the men in those days, and all of those are so powerful that this simple calculator, if you follow these steps, you can compute Bernoulli equation, this and that. So, basically you can do lot of stuff beyond simple calculation like a calculator. So, you annotated all that, and later it took the whole community, like this is in 1800, it took whole community like 200 years to figure her contribution, and basically language is named after Ada language, and this was NVIDIA. So, NVIDIA did one good thing, this 2021 they named after her. We stop basically here today, and in the next lecture we will start talking about little bit of hardware acceleration and mostly about how do we use some of those acceleration techniques for explainable AI. Thank you.